streaming now. And hopefully that's all working. Oh yeah, wonderful, wonderful. But yeah, I guess I'll get into it. I'll also share the webcam here. I can run over. This is our first attempt doing this somewhat portably hybrid math talk. But yeah, welcome everyone. This is the Math and Stats Student Society, and we've got our speaker here, Paras Kumar. He comes from Punjab, India. He's his first year pursuing math phys, and he's got a pretty interesting talk prepared for us about a really interesting physical phenomenon. I think it'd be really wonderful to hear about. But yeah, before we get started, I'd also like to acknowledge that the University of Saskatchewan is on Treaty 6 territory, homeland of the Métis, and we are all treaty people, and I ask that you all learn more about Indigenous peoples on your reading week off. Yeah, with that all done, welcome our speaker, Paras Kumar.
Do I have to stay?
Pardon?
Is it fine if I don't stay in the area?
Oh, you can do however you want.
No. So, good morning everyone. Good evening everyone.
Yeah.
So, before getting into, can you share the screen first?
Oh yes, yes.
Before getting into the topic, I would like to discuss a little bit background, how I approached the problem, and how I was introduced to it. So, in the summer of 2018, so the local committee releases a group of 17 problems which are considered majorly unsolved problems by the IYPT committee. So they will introduce these problems, and every country, and it's a group of 40 countries, and every country has to choose 5 members to represent their country and represent the solutions to these unsolved problems. So the problem I was most fascinated by was the problem number 9 here, the soy sauce optics one. So I will read out the problem statement first. It says, using a laser beam passing through a thin layer about 200 micrometer of soy sauce, the thermal lens effect can be observed. Investigate this phenomena. So when I first read, this was a pretty vague description. I didn't know anything about this phenomena. So I started dwelling into it. I started digging something up. So the first thing I came up was why. So first question is why a specific substance? Why fluorophores? So why the soy sauce substance only? Why are we using? So the answer to that question is fluorophores. So fluorophores are a compounds which absorb light, and then the electron in their ground state gets excited and reach an upper state, but they cannot stay there for a long period of time, so they have to revisit back to their ground state, which means while doing that process they will start emitting light of a shorter wavelength than the usual one. So, and what's specific with soy sauce, the fluorophores in that area has a visual range of EM spectrum, and the concentration of the solution has the same linear absorption, although in the later parts of the experiment we will play around with the absorption coefficients here, and then we can use the similar material like ink and toner, even water, but the screen for the concentric rings we will discuss later were not as quite clear or perfect shape we wanted them to be. So we will discuss the equipments very quickly, the soy sauce sample used, and the Gaussian beam, and then there's power meter and convex lens. And yeah, the experiment I will explain is we have to take a soy sauce sample, and we have to particularly avoid the bubble area. As you can see here on the screen, we have a little bit. So we will consider a very thin area, and the area factor will also play a big role in the later part of the experiment. So we will consider really small part which does not have any bubbles, because the bubble area will affect the concentration later on. So if we include the bubble area, we have to take into considerations two coefficients of one of soy sauce and one of the air bubble inside it, so which complicates our maths, so we try to ignore that. So the basic experiment is, our setup is this: we pass a Gaussian beam through a convex lens. The main focus of the convex lens is to converge the beam through converge the beam to the soy sauce sample, and as the converged beam will hit the soy sauce sample, we will see that our soy sauce sample will start acting as a concave lens due to the heating of its medium. And as soon as it starts acting as a soy sauce sample, we will see the patterns being formed of concentric rings. So I think we have arrived to a problem here. Now we will try to explain why these concentric rings are being formed. So first of all, this is like a block diagram of why of our experiment, and we can also observe a phenomena which, like the number of rings, and there's a linear relationship between the power and the number of rings, and we can also say that P divided by N would be almost a constant of 17. So why the rings are being formed and why this phenomena is happening can be explained by two theories: the diffraction theory and the heat exchange theory. So, and in this paper, we will try to connect these two theories, because the heat exchange theory in alone is a pretty complicated version. We can, it's a big of, we will get a pile of equations and which we won't end up solving. So diffraction theory is our main to go, but through diffraction theory we will be touching on the heat exchange theory. So first of all, we have to understand the thermal lens. So it's non-linear optical effects. So there are Curie effect and the Kerr effect. These are non-linear effects too, but those are those are from a point of view of an electromagnetic perspective. This is from a thermal perspective, which means when there's a change in temperature, that will lead to a change in the refractive index. A change in temperature will lead to a formation of a thermo-optic coefficient, which we can see on the screen is dN by dt. And this equation pretty much sums up how the change in temperature will lead to a change in the refractive index. And then we have to define what a Gaussian beam is. So in our experiment, we have defined, also there are, in papers there are two types of, can you show this?
Oh yes.
Okay, so scientists have, like, there's a bit of discrepancy between the papers and the literature in itself. Some scientists assume there's a transition from e squared to e to the power 1, and some assume e to the power e. So that doesn't help us in the major equations, but when we dug into the integration systems, and we will see this kind of gap between these things, and the modified Windry solution tried to bridge this gap. But basically, we can define the intensity of a Gaussian beam by the following function. And we can see here E plays a big part in this, and this graph can explain a Gaussian curve, which we call a Gaussian profile. So yeah, can you show this? Okay, so here we can also see that this is a Gaussian profile. So Gaussian profile it decreases and increases before getting through a cavity, and when it gets through a cavity, it does the same thing again. So it obtains two maximum points at root 2 omega naught, which you can see, and we can also calculate that by the equation in the previous part when we put the lambda z by 2 pi omega naught square equal to 1, because that's the maximum value it can achieve. We can also, and that specific distance is called Rayleigh's distance. You can see experimental results here, and compared to the one which were obtained earlier by other papers, and we can see a huge bump in near the x-blade position 0.2. That will be an important role, playing an important role in the later section, which is due to the gravity formations. So the only distance here, the zeta distance here is called the Rayleigh distance, at which there's the intensity of the beam is maximum, and also so there was a paper proposed in which Gordon proposed that the focal length of the induced thermal length, which is our soy sauce sample at this point, would be inversely related to the thermo-optical coefficient, which means if dN by dt, which is the thermo-optical coefficient, the change in is less than 0, it will form a because all other form a concave length, because all other quantities here are definitely positive, and if it's greater than 0, it will form a convex length. In our case, we can induce this by experimental also, and we can prove this theoretically also. We get a concave lens. The soy sauce sample will act as a concave lens, and so we'll talk about some spherical lenses. So we can see, we can define the optical path length as k and L, where k is 2 pi by lambda, and this is, so we are getting into diffraction theory. So diffraction theory can be summed up by one line. Sorry. So it's really, when we see a perturbation in a system. So before entering a soy sauce sample, there is no phase lag in the beam, but when this is an induced thermal lens sample, the soy sauce sample, after acting there was a perturbation of phi RT. We observe this through, and this leads to the formation of the thermal lens. We will try to connect why this happened and how the phase difference between the wavefront after getting out of the thermal lens, the soy sauce sample, and before getting into the thermal lens, or the soy sauce sample, why this happened. And we will, so in the gain medium, as you can see here in our presentation, that before entering there's no phase lag in the wavefront, and after exiting the wavefront there's an additional phase lag of phi RT. And this can be explained by the Bell's theorem also, which simply states that the additional phase lag will result in concentric rings. So our concentric rings can be explained by this simple equation, and here n stands for the number of rings. So this clearly proves why we are getting concentric rings. And there's also a method called speckle cell phase modulations, which also results in the similar phenomena and explain the same thing. So we can modify our equations according to a need. So we can write as phi, and we have defined here. We have to be careful here. We are taking dN by dt as negative because we have proved that our lens is acting as a concave lens. So we can plug in the value of nRT as n0 minus dN by dt, where delta t r into delta t RT. So if we plug the equations into the above equation, we will get a following result. So we will multiply both sides by 2 pi by lambda, And this equation is proof that the change in temperature is leading to a change in the phase lag. So the phase lag here can be directly linked to the change in temperature. So we have connected the heat exchange theory and the diffraction theory through one equation. And now getting on to the metric systems. So anything for a Gaussian beam or any other beam, the Q parameter is a really important parameter. We can deduct any information we require about a beam from its Q parameter, be it the wavelength, be it the waist, be it the radius of curvature at any specific point. This can be deducted from a Q parameter. So we define we can also prove why this equation exists through the Gaussian equation, previous Gaussian equation, but it's not really worth getting into. So we'll say we'll define this, and we'll try to play around with this. And okay, so before I go forward, we will consider any, be it any form of cavity. Here I will define the cavity as a lens or a medium which will change the refractive index, the radius of curvature, or the wavelength of a specific beam. We'll define that as a cavity. So before entering a cavity, there's a specific wavelength to a beam. But after it enters cavity, the Q parameter changes, because either this wavelength changes or other factors like radius of curvature instantaneously changes after it exits a cavity. And because cavity modifies a Gaussian beam in our case, or any other beam, modifies its wavelength, its radius of curvature. So the Q parameter changes. So our equation, which is relates the two Q parameter with each other, the Q before entering and the Q after it entered the cavity can be related, and this is called the ABCD law, and we can also write in different forms. And then we can also, so here the ABCD is a simple matrix which can, for a lens, it's the 1 0 minus 1 by f1, and for the free space it's 1 L 0. So instead of for the induced thermal lens, the f would be replaced by the focal length of the same, and for the effective matrix for the system. Now this is an easy system. We have removed the convex lens in this system because we wanted to ease our calculations. In this system, we can calculate, but we have to calculate from the left side. So from the screen, the D2 one will come first, and the effective matrix is just the product of the distance. Then it comes the focal length, and then the distance. If we had, let's say, we wanted to make a complex system, we would have added something like this. So this would have been like, if we have included our focal length for the convex lens also. So the reason we decided to deduct the convex lens was because it was really it was trying to just concentrate the beam. We can form the rings without the convex lens also. The only problem is the rings won't be that clear, the rings won't be that sparse, and maybe it will affect the number of rings because more energy will be needed to make the same amount of two rings as we needed to make 5 rings, let's say. So maybe it will affect the number of rings, and it will affect the clarity on the screen, but it won't affect the general system even if we remove the convex lens. So I'll just go in the appendix section. So yeah, we can prove, and when we do this, we will get a matrix of something like this. And so it's a basic proof. If we approach it so why our approaches to infinity can be explained at focal length. At focal length, r will approach to infinity because the theta for this will be a 90-degree angle. So if r approaches to infinity, we can assume this as minus lambda by pi omega squared, and we can then do our further calculations. And then we can compare two after cavity and before cavity equations and just multiply them on both sides. Here we will try to compare these equations. So you have to take in mind that Q1 into Q2 will be a product of imaginary numbers. So we can compare the C and B part, and we can compare the D and A part. So while comparing the D and A part, we can deduce this this equation, and after that we can play around with the matrix a little bit, and we'll get our answer for this is minus 1.63. That's exactly what we hope for our focal length to be negative, so we can say it's a concave lens. Now we can safely say it's a concave lens. And now we'll get into the factors which will affect the system. So first one will be the concentration. To explain the concentration, we have to explain the Beer-Lambert's law. So the Beer-Lambert's law is exactly says that the concentration of beam will change logarithmically in the power of 10 with respect to the incident intensity of the beam. And we can also compare these equations, and we can assume the graph would be in the power 10 to the power mx plus c. So that's exactly what we got in our paper. And then the variation of focal length, we can also, the complex system I showed you, we can put in the values for complex system, and we can deduce that focal length will vary on a various basis if we keep on varying the focal length of the first lens, the convex lens. So, and then the effect of gravity, the most important, which was not observed earlier by any paper. So we tried formulating a concrete theoretical basis for it, but we couldn't find it. But while doing our experiment, we found the bulge, and the only reasonable explanation our research team found was that this bulge is due to gravity. So it's not like any other electromagnetic effects. In this effect, we have to wait long time for the formation of the rings. While waiting for that long time, the density of the for the induced sample we took, the soil saw sample, due to gravity, the concentration will keep on changing as the gravity will pull down the particles, and so we never took that into account. But this bulge is the proof that the gravity affects the induced thermal lens, and that we were able to conclude that. And we can also vary the distance between the soil saw sample and the screen. And if we want to make it more complex, we can do it with the complex system. And when we saw that, we will found a linear relationship again in terms of a specific constant. And we found that if the convex lens in the complex system, if the convex lens is placed at a focal length of the induced thermal lens, we'll found the maximum number of rings being formed with n equal to 9, and that's the maximum number of rings were formed during when we place it at. So, and also the spatial self-phase modulation, which can be explained by the Bell theory. Thank you.
Oh, is that your whole talk?
Yeah.
Yeah, thank you very much. As is customary in MS Cubed, always applaud our speakers. So anyone in Zoom, you can join in too. I don't know if shows good video. Yeah. Nice. But yeah, if there are any questions, of course the chat is open. Paris is very ready to hear some feedback. I think it is really interesting how you do end up with like shooting out circles in the end. Like that is I don't know, it's just always gonna be kind of surprising to me. Yeah. Does how much do things change if you use a different thing than like soy sauce for?
So like we try to do it with water, but with water we'll almost get like a vague circles. So the circles will like overlap sometimes. It's pretty interesting to see. For ink and toner we'll get the same amount of circles. But for any other material which does not have like many condensed quantity, there's no need for doing that.
Yeah, thank you. But yeah, give it a bit more time. Hopefully people are, or give people a bit more time to type things out. But yeah, how did you end up getting like the gear to do the experiment? I'd kind of like to hear about that a bit.
Like the equipment and everything?
Yeah, to like test it out and record
so
the data.
Like I had to travel like across the country on a completely different side. So I live on the east side and I had to travel to the west side. And I only got the time for one. That's why you will see that like there are many incidents in which there are only 3 data points, like this one. There are only 3 data points. That's not because I was lazy, that's because I had lack of funding. And I got only 1 day to do all this experiments, and so I had to like make work with 3 data points.
Yeah, do what you can with what you got. But yeah, I think that's a pretty cute little talk. Glad that you came out here to talk to us about that. I think that's very interesting material. Of course, it's always exciting to see a bit of linear algebra pop up here and there, even if it's just like make the data look nice and presentable. Yeah, Matt says great talk, thank you. But yeah, I'll do one more applause for our speaker. But yeah, I hope you all have a great reading week and get lots of rest. I know I'm definitely feeling the need for some rest now. But yeah, and then after reading week, we'll have a pretty slow rest of the semester. Yeah, thank you all very much.